differential equations, the first lesson is just giving you some names. When you look at equations, you kind of got to be able to categorize them. Just because you see an equation in algebra, you can usually solve for x, right? Not the case in differential equations. Every situation warrants a totally different situation, totally different set of rules, totally different set of formulas, as you're going to see. The three things you need to think about are type, order, and linearity when you look at them. And so we're going to look at ordinary. The types would be ordinary and partial. And I think, how many of you are multivariable right now? You do partial integrations with, yeah. So you're used to this kind of, is it a Greek? Is that a schwa, or what is that? What do they call that? Oh, okay. But anyway, this means a partial derivative with respect to y. And so this is a partial differentiation. We'll do a little with that, but mainly we'll look at the ordinary. So ordinary is just your du, dx, dv, dt, whatever, with x's and y's. No partials. So ordinary, partial would be the types. The order is simply the greatest power of the derivative. Okay? So the greatest power of the derivative, if you have d squared y dx squared, that's going to be the second order because that's the highest power you see. If you see a dy dx and it's cubed, that doesn't mean dy, the third derivative. It just means it's the derivative with respect to x cubed. So first order for that. And so type is partial versus non-partial, ordinary they call it. Order is just the highest power of the derivative. And then the last thing that we have is the linear. I have that here. Linear and nonlinear. Linear, if you think of a linear equation, it's y equal mx plus b, right? You notice that the variable has a constant next to the variable, right? So the same thing is with a linear differential equation is you have a derivative with a constant or a single variable. And whenever you mix more than one variable, for example, these are linear, x dy, y dx. Y looks like a double prime there, so it'll be the second derivative and so on. These are going to be linear, and nonlinear is if you have something other than a y prime. Instead of an x, you have like a y next to it, or a y squared, y double prime. That's the harder one. Here's an example where they say it's nonlinear, because instead of this being dx squared, like that, they have, that would be the second derivative times y. You need to have this with respect to x. This can only be a constant or an x. As soon as it isn't, then it's going to be nonlinear, and it makes it a lot more complicated. D cubed y dx cubed, that one would be fine. These are going to be linear, but these are nonlinear. Oh, excuse me. This one's not linear because the y is a power other than 1. So I think on this slide somewhere here is they have two things to think about whether it's linear. Y is to the first power. So you can't have y squared, then it's nonlinear. The other is the coefficient has to be an x or a constant. So this has to be an x or constant. And then y can only be to the first power. Can't be more than that. So these two would be nonlinear. And then let's go to the homework. That's all right. So you're just going to do 1, 3, 5, 7, 9. All you have to do is tell me linear or nonlinear, and then hold off on the verification part. We'll get to that.